In this video, we're going to be learning about the second major periodic trend, and that is a concept that we call ionization energy. Now, from the structure of the word ionization, we can infer that this is a noun and that the verb form of this word means to ionize, which refers, of course, to the process of taking an atom and turning it into an ion. Now, there are two ways that this might happen. If we have a non-metal atom, non-metals traditionally gain electrons more easily in order to ionize, whereas if this atom were a metal, it would conversely lose electrons in order to form an ion, which makes the concept of ionization energy difficult to measure if we're talking about two different processes depending on the element. So instead, we focus specifically on one of these processes here, which is why ionization energy in chemistry is defined as the amount of energy that is required by a specific element in order to remove or lose a single electron from that atom. And even though metals are traditionally the elements that lose electrons more easily, we can also apply this same concept to non-metals, even though non-metals don't often lose electrons, which makes it a relatively rare process. Now, what exactly is meant by energy? Well, it's actually easiest to take a look at a compare and contrast example between one metal and one non-metal in order for us to understand what exactly is meant by energy. Now, if we consider sodium, the easiest way to compare sodium and chlorine is actually to compare the Lewis structures. So sodium as an element has only one valence electron, whereas chlorine as an element has 7 valence electrons. Now, because sodium only has one valence electron, losing one electron is much easier than gaining 7 electrons. Now, if a process is easy to do, does it require more energy or less energy than a process that is hard to do? Well, obviously that would be less energy, and because the process of a metal like sodium losing one electron is relatively easy to do, something that is easy to do requiring less energy means that sodium, like most metals, has a comparatively low ionization energy because a process that is easy to do requires less energy in order to make it happen. Now, conversely, chlorine has 7 valence electrons, which means that gaining one electron is much easier than losing 7. Simply put, does chlorine want to gain electrons at all? That answer would be no, because it is much easier to complete its valence shell by gaining an 8th electron and forming a full 8 electrons in its valence shell. Now, because of the fact that chlorine does not want to lose electrons, in other words, that it's very difficult, this conversely means that chlorine as a non-metal will have a comparatively higher ionization energy than a metal like sodium. So this is one predictive trend that we can use before we even look at the periodic table, but a lot of the trends become very obvious once we compare them to atomic radius. Now, as we've learned from the atomic radius video, the farther down the periodic table we go, the larger the radius, meaning the larger the distance from the nucleus to the valence shell of an element is going to be. Now, when we consider that ionization energy is the process of losing a valence electron, let's take a look at our alkali metals. So lithium is our smallest alkali metal because it only has one valence electron in the second shell. Sodium is larger than that because its one valence electron is in the third shell. Potassium has its valence electron in the fourth shell, rubidium in the fifth, and cesium, the largest of the relatively stable alkali metals, has its valence electron in the sixth shell, farthest away from the nucleus. Why is this important? Because the nucleus is the location of all of the positive charge in the atom. Now, as the valence electron gets farther away from the nucleus, does the attraction between this electron and the nucleus get stronger or weaker as the electron gets further away? Well, that answer would be weaker, because the farther away the negative charge is from the positive charge, the harder it will be in order to attract. Now, if this attraction between the nucleus and the valence shell is weaker, does this require more or less energy in order to remove? Well, that answer would be less. A weaker attraction means that it takes less force in order to separate this electron, meaning a lower ionization energy. And this is why we say that ionization energy increases upwards. Because when we go from bottom to top like this, atomic radius is going to decrease. In other words, the valence electrons are going to get closer, not from the, but to the nucleus. And as valence electrons get closer to the nucleus, they become much harder to lose, because the valence electrons are now closer to the positive charge that is holding them in place. And that's why the smaller an element's radius is, the smaller an element's atomic radius is, the harder it is to remove a valence electron, and therefore the more energy is needed in order to pull it away. Hence why ionization energy increases upwards. Now, we can also use this trend by looking at atomic radius if we go from left to right. So we can say that ionization energy increases when we move rightwards like this. Now, why is this? Well, for the same reason. So in the atomic radius video, we explained that as the number of protons increases, for example, boron has 5 protons, carbon has 6, nitrogen has 7, oxygen has 8, and fluorine, right before the noble gases, has 9. Now, the more protons an element has, the stronger its positive charge is going to be, which means that the stronger the positive charge is, the more it is going to pull the electrons in the valence shell closer to the nucleus. And as we've already established, as valence electrons get closer to the nucleus, they become harder to remove. So for the same reason, atomic radius, when we move from left to right, decreases, and because of the fact that valence electrons are closer to the nucleus, this makes it significantly harder for them to remove. But we don't even need to look at atomic radius in order to understand this trend. All we need to do is look at the number of valence electrons that each element in each part of the periodic table has. We know that the metals on this side here, well, technically this side, because aluminum is a metal as well, we know that the metals preferentially lose electrons because it's much easier for an alkali metal to lose 1 than gain 7. Or it's much easier for an alkaline earth metal to lose 2 than it is to gain 6. So comparatively speaking, metals are going to have a very low ionization energy, whereas for the halogens, it is much easier for chlorine and fluorine to gain 1 electron than it is to lose 7. So because of the fact that when we move from left to right like this, the valence shell becomes closer to being full, this means as the number of valence electrons increases, the electrons get harder to remove because the closer we are to achieving a full valence shell, and therefore as we get closer to achieving a full valence shell, the ionization energy, the energy that is required to remove an electron, is going to increase drastically, which is why the nonmetals, especially the noble gases, have the highest ionization energies on the periodic table. Before we address the final periodic trend, and also the most important one, electronegativity, see if you can use your knowledge of ionization energy to answer the practice questions below, identifying which elements have comparatively higher and lower ionization energies, and see if you can answer a few case studies that uses this to explain why elements behave the way that they do.